Hey guys, welcome back, and I hope you watched my previous video on this topic of Light GBM versus XGBoost, where we just introduced the concept of Light GBM and used Wisconsin breast cancer data set for binary classification, whether a data point corresponds to malignant or benign. Now, it was a small data set, so let's actually jump in to a slightly bigger data set, which is image segmentation, right? I mean, here we have millions of pixels that need to be classified. So hopefully we'll have enough data to compare both LGBM and XGBoost. Again, remember, semantic segmentation is nothing but segmentation of every pixel in your image. That's it, instead of this entire image. Okay, now for those of you who did not watch my previous video, I definitely recommend doing that. But let me quickly provide you an overview. Light GBM is very similar to XGBoost in that it is a gradient boosting methodology which has been optimized for speed, so it's fast, it's distributed, high performance gradient boosting framework. Okay, it's based upon decision tree algorithm. So with that knowledge, let's go ahead and jump in. And one thing I'd like to highlight is there are many parameters that can be optimized, and you need to learn a bit more about what these parameters are and how they can influence your model. That is not something I'm going to do in this video, and maybe in future, but not in this video. Okay, so let's jump in. Now, before getting to the code, let me just define the problem that we are trying to do, right? I mean, we have an image like this, and we are trying to segment every pixel, meaning I want to label this, this dark region as background. I want to label this medium gray level as, I don't know, pixel 1. In reality, this is a sandstone, so this represents quartz. And this represents like void, the dark area. The bright represents a heavy mineral, probably pyrite in this case. And this textured area right here, this area represents clay. Okay, this is very difficult to segment. That's why using machine learning is almost necessary to segment these regions. So we have these 4 different classes here. So the easy one is the black one, right? The dark one. The bright one is also easy to segment. And this area, we have enough of it, so it's also relatively easy. But these type of regions, we don't have much of it, so this can be a bit of a challenging to segment in an automated way like this, okay? Now, I have labeled at least, how many images did I label? Let's look at the folder structure here. I have 3 folders, test images, obviously to test it. And let's look at it. I have 1 test image and corresponding mask where I labeled every pixel. And I'm going to use this as ground truth when I compare how well my algorithm is performing. Okay, so that's, in fact, if I open that, you'll see that, okay, every pixel is kind of labeled here. Okay, and what are the labels? The labels are, I don't know if you can see up here, but the labels are 1, 3, 4, this is probably 2. So 1, 2, 3, 4. These are my labels. And how did I label that? I mean, even if you look at my labeled image right here, how did I label it? Okay. For that, if you already have a way, fine. If not, go to www.appear.com, A-P-E-E-R, and it's a free sign up, and you can annotate your images. Okay. So I'll leave the link in the description. Now getting back here. So let's minimize all of these so we can focus. Okay, so I have a folder for test images. I have train images. I have 8 of them. Each image is 996 by 1024, like 1K by 1K, each image size here. And corresponding masks, right? Mask is also 996 by 1024, but remember, not every pixel in the mask is labeled, which means I have to drop all the pixels that are not labeled for training, because they don't mean anything for training. Okay, so this is the goal, and I have done this quite a few times in many videos, but again, I'm explaining all of these for those of you who haven't watched those, or who if you forget exactly what's going on here. So with that knowledge, let's jump in. Now, here is the code left over from the last video where we did our Wisconsin breast cancer data set and realized that, okay, LGBM and XGBoost take very similar times, or maybe XGBoost is a bit faster for this data. But when it comes to accuracy, LGBM did much better job compared to XGBoost. Now, This is exactly, we are trying to do very similar exercise, except instead of sending a structured data in a CSV format, we are going to use images, extract features, and then send those features through these two algorithms and then see how well things go. So let's clear everything from the last time, and let me clear the screen, and let's save this and exit this and focus. Let me go ahead and zoom in so you can see it a bit clearly. Okay, I hope that's good. So we are doing LGBM. What's the goal? Versus XGBoost for semantic segmentation. In doing this process, you'll also learn how to use LGBM for semantic image segmentation. Okay. Now, these are the images I cannot share with you. These are somewhat, I mean, these don't belong to me. So, but the process, you can do it with any of the public data sets, any data set where you can do semantic segmentation. Okay. So the required libraries, again, to install your XGBoost, pip install XGBoost. In fact, I should have copied and pasted how to install LGBM. It's basically LGBM from my last video. Okay, so let's import all the libraries that we imported in the last video, and let's also import keras.models.model. Why? Because I'm going to use pre-trained VGG16 that has been trained on ImageNet database. I'm going to use those weights for feature extraction. You can use any feature extraction. You can write your own Gaussian filter, edge detections, and Gabor filters, and any of these, right? And put all of those together as feature. Please watch my video 67, I believe, 67B, to understand what I'm talking about. But for now, let's use VGG16 as feature extractor. We're not doing deep learning. We are using pre-trained deep learning model without the classifier part, only the convolutional part as feature extractors. Okay, that's it. Only the first two layers, that too. And I covered this in many videos. So let's move on from here. Okay, so we are going to use VGG16. So I'm going to import that also. And just a sanity check, what directory am I? Okay, so in images, there should be test image, train images, and train masks. Great, I'm all set. Now I'm defining my size of X and size of Y. Why? In case my images are of different size, I can resize them. That's all. In this case, I'm not going to resize because I know that they're okay, but this is always a good practice in case you download your images from somewhere and they're all different sizes. So let's prepare our data. I'm going to capture all of my images from these folders into train images list and train masks list. Okay, so that's what we are doing. And let me run these lines of code here, which means I'm reading every image in that path using OpenCV, resize them to whatever this size in case the size is different, and then converting them to RGB to BGR. Again, that's an optional step. You don't have to do that. And after all of this, my train images is a NumPy array of size 8. As you can see, NumPy array of size 8, and each image is 1024 by 996 by 3. And I have 8 of these images. Okay, 8 images is okay for now because I have a lot of pixels for training. Now, this is a list. Lists usually don't work very well, so I'm going to convert that into NumPy array, which makes it easy for us to do math on these arrays. I'm going to do exactly the same for masks. Okay, so at the end of this, we'll have a NumPy array of images and masks. That's it. Okay, now I'm redefining my train images and train masks as X-train and Y-train. Remember, in all of these machine learning exercises, we just use the term X-train, Y-train. So just to make things intuitive, let's do reassign these names. And my training masks are all grayscale masks. So if you look at the dimensions here, train masks, it says 8 by 1024 by 996. I want to expand this dimension by 1, so the dimensions are the same for both train images and train masks. Okay, so that's exactly what I'm trying to do right here. Let's run all of these lines. So now you can see my Y train is 8 by 1024 by 996 by 1. Again, I covered this in many videos, so I apologize for those of you loyalists who watched all my previous videos. So now we are all set to extract features. So for that, we are going to use VGG model. So first, let me import VGG with ImageNet weights. Okay, so this is a pre-trained model. Let's just import this without the top, which means without the classifier part, without the dense layers. Okay, and let's go ahead and import it. And while importing, change the size input shape of my model to size X and size Y. This is the reason I defined it up here to 1024 by 996. Otherwise, by default, VGG16, I believe, accepts 224 by 224 pixel input images. Okay, so we'll see that. So let's go ahead and do this. And it should be imported. Now it's imported. Now, how do we know? Let's go ahead and print the summary. Okay. So if you print the summary, let's go back up. You see that this is 1024 by 996 by 3, and then it adds convolutional layer 1. And after that convolution operation, you'll get 64 features as a result of it. And then after convolution 2, you get 64 features. But then once you do max spooling, right, you're max spooling with a certain kernel size, then it changes the dimensions here, changes the dimensions, and so on. And these are all the number of parameters that can be trained. If you go down, it says 14.7 million parameters. All of these are trainable, but we don't want to train them. We don't want to train them. We want to use it as a feature extractor. That's exactly what these lines are. For each of these layers, make it not trainable. So layer.trainable is false. Okay, that's exactly what we are doing. So if I print the summary again, you'll see exactly the same thing. Okay, same structure, but all of these are tagged as non-trainable. But all of these layers are not useful for us. For us, the only useful layers, for example, are, let's only take the first 3 of these, like 2 of these, because here the image size changes. And let's just take the output from this layer as feature or feature extractor. Okay, so that's what we are trying to do here. My new model is basically this model that I just defined, except just get the layer up to block 1 conv 2, right? Block 1 conv 2. This is the layer where I want to chop it off. So that's exactly that line. And now if you print out the summary of new model, you should only see the input layer, the first convolution, the second convolution, and the output from this is basically our 64 features that we are going to take it into XGBoost or LGBM. Okay, now how do you extract features? Well, we defined a model, new model. You just need to do new model.predict. Predict on what? Predict on our training data set, right? The data set we just defined up there. So this is our features, and this will take a little bit of time because we are loading a whole bunch of images and extracting features. Okay, and after this operation, our features up here, you see our features, we have 8 images, each 1024 by 996. And for each image, you have 64 different images or channels or features. Obviously, that's what we expected to see, correct? I hope this makes sense to you. All we did is extract features from each of our 8 images. That's it. Now, do you want to see how those features will, look like? So let's go ahead and plot them. And if I go to plots, once this is done, you should see these are all different features. It's tough to see at your magnification or at this magnification, but go ahead and print each one of these out to see how the response looks like. Again, this is not a tutorial on feature extraction, which I've already done. Again, please subscribe to this channel to be updated with these type of awesome videos. Okay, now we have features, which is our X values, our segmentation, our label is our Y values. That's what we are going to define next. Okay, so our X equals to features. Okay, and our features, again, in these tree-based algorithms, you cannot just take 2D as input, right? these are not convolutional filters. So, these are classifiers. Remember, even in deep learning, you're doing convolutional filters, but at the end you put you convert that into a 1D vector that can be that you can feed to the dense layers. Sorry, I was losing my mind. To the dense layers and the classifier. So exactly the same. You have to reshape here into one-dimensional vectors. So that's what we are doing. If you look at the shape of X, again, your X is 8, 1024, 996, 64. Let's collapse all of these. So that's what we are trying to do here. So you actually have these many rows and 64 columns, each column representing one feature. Okay, so each pixel, 64 features. Think of it as that. So we have 8 images, 1024, 996 pixels. So when you multiply all of these, you get like for each pixel, you have 64 of this. This is a lot of data, okay? But bulk of this data is useless. We'll find that out in a minute because we haven't labeled, we have only labeled parts of it. So let's only take the regions where we labeled and drop everything where we haven't labeled. We'll do that in a second, but let's go ahead and reshape Y also here, okay? So let's do that. So when you do that, my Y values are, again, all the pixels, where each pixel represents either 0, 1, 2, 3, or 4, sorry. We have 0 being unlabeled pixels, 1, 2, 3, 4 being the labels for each of these 4 regions that we have, right? So 0 is all this dark area, 1, 2, 3, 4 are the 4 regions that we have here, okay? So hopefully you're with me until now. Now I'm going to combine this X and Y into a single data frame so I can remove all the values equal to 0 from both of these. Okay, that's exactly what we are trying to do. So combine these into a single data frame called dataset. And now if you just look at the unique values here, the unique values we have in this dataset, that entire dataset, are 0, 1, 2, 3, 4. Okay, now if you just look at how many of each we have, you can see that our 0 is 7.8 million pixels, all having a value of 0. We don't want to train our data on this, but then we have 122,000 corresponding to label 3, 92,000 label 1, 58,000 label 2, 24,000 label 4. This is not balanced actually. Watch my video on how to balance data sets to see if you can balance this in a way by oversampling, undersampling. But again, let's focus. So once we have this, our goal now is to drop all this. So that's the next line here. Dataset is dataset where my column label equals to 0. So now when you go ahead and and let's do this. Let's go ahead and print this one more time. Now you should not see 0. You should only see 1, 2, 3, 4. Again, sorry to go through all these basics, but you never know where you are going to learn a little gold nugget that's missing in your knowledge, right? Okay, so now I'm just redefining X and Y, that's it. So the reason I combined X and Y is it makes it easy for me to drop the same rows where my value equals to 0 from both X and Y, that's it. Now I'm splitting my X and Y from this data set. So no need for further explanation here. This is basically splitting this and converting this into NumPy arrays, that's it. Okay, let's do exactly the same even with our validation image. So if you remember, we have a folder called test images or validation image. So let's load this test1 image as our validation image and test1 mask as our ground truth so we can compare both. Okay, so test1.image, exactly, I'm loading them as my input images. And then I'm going to extract features from it. Remember, new model.predict gives you the features and reshaping it. Okay, all of this should be pretty straightforward to you. And once we have the validation image, let's go ahead and load the truth image. So loading all the data would be done at this point, and then we'll focus on gradient boosting and all that stuff. Okay, so let's load the ground truth image. And again, the truth image is, where is it? The truth image has these many pixels and the values go from 1, 2, 3, 4, right? The true pixel values. Okay, now we are coming to the actual part where we will do the model defining and fitting. This will be the fastest part, okay? Not many tricks. I did this again 2 videos ago, how to do this, but again, let's redefine our gradient boosting, our XGBoost, import it as XGB. And then define the classifier. You can define a whole bunch of hyperparameters if you want in here. I'm just leaving it as is, okay? So let's go ahead and do that. And model.fit, let's actually go ahead and fit this. This will take some time. I'm doing this so you can see in real time how long it actually takes. Okay, maybe I'll have to pause the video because it may take longer than 30 seconds or 1 minute, and it's not a good use of your time. But at the end of it, I'm going to print out the execution time anyway. So let me go ahead and pause this. It's not a good use of your time staring at paint dry here. Okay, so it felt like almost a minute. So let's go ahead and print this out. So execution time is obviously stop minus start. Let's print it, and it's about almost 2 minutes, 1 minute 52 seconds, let's say. Okay, let's compare this with the Light GBM, obviously. Let's go ahead and predict it. Okay, so what did we call this? XGB model, right? So dot predict what on my validation feature, right? Again, just to quickly remind you, we are going to this is our input. Okay, so let's come down, let's go ahead and predict, so we can print out accuracy. Let's save all the accuracy part to the last, because it makes it easy for us to compare. So let's not print it out yet. Okay, and let's also calculate these mean IOU, intersection over union. Remember, when you're doing semantic segmentation, accuracy means nothing. You may be 99% accurate on a region that's like 99% of your image, but what's important is a small area, and you may be horrible on that, right? So intersection over union gives you a nice idea on exactly how accurate your semantic segmentation is on different regions that you're trying to segment. Okay, let's do exactly the same exercise for Light GBM, LGBM, and let's define the parameters, and let's run these lines, right there, and you'll see how much faster this is, probably real time, right? I mean, when I hit this, let's see, there you go, it's doing something. How many iterations we put? Like 50 iterations, it's already done. Well, is it any better than XGBoost? That's what we are going to see. And also, I'm using GBDT as boosting type. If you use Dart, I think the accuracy improves, but let's not defocus for now. Okay, so what's our execution time? Probably a second or so. 6 seconds, okay, not bad. Now let's run all of these. Oops, sorry, I always do this. Let's run all of these lines and finally print the summary. Okay, so just predicting on our validation image and all that stuff. Okay, so finally let's clear this up and print out the report. There you go. Okay, so how long did it take for LGBM? 6 seconds. For XGBoost, 1 minute 52 seconds. So obviously the speed wise, LGBM kicked XGBoost's butt. And when it comes to accuracy, LGBM 94.1%, XGBoost 93.8%. So obviously LGBM won that. And mean IOU is 79.8, right? Intersection over union, and 79.1 for XGBoost. So in all of these fronts, Light GBM actually did an amazing job. In fact, let's do one final thing before ending the video. Instead of GBDT, let's do Dart and see if that improves the performance any further. So this should be pretty quick. So let's go ahead and do this. Dart for boosting apparently gives, let's remove everything and run this entire code one more time. I'll pause the video because XGBoost is small. I really want you guys to see the result with Dart and see if that actually improves accuracy. I don't know. I'll find out with you. I'm hopeful that you're also equally curious. Okay, so let me pause this so I don't waste your time. Okay, so finally it's done after almost like 3 minutes or so. And let's look at the summary. Execution time for LGBM, 5.6 seconds. Okay, so pretty quick. And for XGBoost, it's 1 minute, almost 48 seconds or 47.6 seconds. Okay, so definitely LGBM is faster even with this Dart boosting. And accuracy with that's a pretty big improvement actually. With LGBM is 94.3, 93.8 here. What was the accuracy with the other? Oh, sorry. Previously we got. Sorry to go through all of these. I should have copied these values. Where is it? So we got 94.1 and 79.8 previously. Okay, 94.1, 79.8. So here we got 94.3 and this is 80.2. So a slight improvement, obviously. Okay, so 94.3. The point here is it's better than XGBoost, much faster. So if you have loads and loads of data, lots of data, LGBM seems to be not only more efficient, yeah, but also more accurate. So this is the summary based on at least these two data sets that we have done in the last couple of videos, right? The semantic segmentation and breast cancer data set. So now you have various ways of picking your classifier. I used to be a great fan of random forest. I still am, but after using LGBM for a while, for the last few weeks, I've become a super fan of LGBM. If you want traditional machine learning, if you don't have lots of data for deep learning, LGBM seems to be the best choice. XGBoost is not bad, but then again, it's using a lot of resources and it's a bit slow. Some challenges maybe traditional machine learning cannot handle. That's when you go to deep learning. Okay, deep learning is my last resort and I hate it whenever I need to do it. But if you have annotation needs, go to appear.com and you can use deep learning, you can use traditional machine learning, anything on that platform, and it's free. Thank you very much for watching this video, and in the next video let's have a quick look at feature selection. Okay, you have many of these features. Is there a way you can actually rank your features and select, okay, these are the best ones, and let me go ahead and use that. Okay, so stay tuned for that video, and until then, please subscribe to this channel.